Hi, I'm Andres Ramos from Queen's University, and I'm going to talk about the estimation of energy absorption capability of arm using force myography for stable human-machine interaction. Human-machine or human-robot interactions improve humans' mobility, accessibility, and health. Some applications include telerehabilitation, haptic training simulators, and assistive devices. However, safety measures need to be addressed when applying robotic-generated forces that may put patients at risk. In a telerehabilitation system, the amount of force that is transferred from a therapist to a patient needs to be of an amplitude that is efficient to work, as well as the amount that the patient can handle. The safety and stability of interactions depend on robot and human dynamics, but only arm dynamics change constantly according to muscle contractions and joint angles. Thus, the arm can inject or absorb energy from the system. This active behavior has the potential to induce instability and pain, or even injuries. Therefore, we need to understand these changes in arm dynamics to be able to determine the safety and stability boundaries in telerehabilitation systems. Human-robot interactions are stable if the dynamics projected to the patient are passive. Humans can maintain stable contact with passive objects and even stabilize unstable systems by natural modulation of arm dynamics. As a result, stability boundaries can be relaxed for increased performance, allowing just the amount of energy that can be absorbed by the patient's arm. However, we still need to reduce energy flow to the patient to guarantee safety and stability. Some methods to address these, called stabilizers, are the addition of damping, scaling, and capping of the interaction forces, but their implementation reduces performance, so they should be used as a last resource. Therefore, the efficiency of a telerehabilitation system depends on how accurately we can estimate the arm's energy absorption capability in real time. We use excess of passivity, or EOP, as a metric to estimate the energy absorption capability of the arm. EOP captures nonlinear dissipative properties of the human arm that would need real-time modeling of its dynamics, as it changes according to muscle contractions. In 2017, Atashar and others developed a graph-based method to estimate EOP. It can be obtained by stimulating the arm with a robotic manipulator for a few seconds and measuring the non-voluntary reaction force and velocity of the interaction. We are working on improving estimations by adding muscle activity of the upper arm, specifically force myography of biceps and triceps, which we think can increase the amount of biological information that determines arm dynamics. From now on, we'll refer to our method as full arm FMG. We conducted our experiments on the Q-arm, a 1 degree of freedom manipulator developed by the Biorobotics Laboratory at Queen's University for research purposes. The setup consists of a 400-watt Maxon brushless DC motor equipped with a resolver for position tracking. It can provide a maximum continuous torque of 16 newtons per meter. An anti-gamma force and torque sensor is used at the base of the handle to measure interaction forces. 4 Texcan FlexiForce A502 pressure sensors are used for measuring force myography at the hand, biceps, and triceps. We used non-elastic bands to keep the sensors fixed at the upper arm and maintain positive pressures. All sensors were calibrated at the start of each experimental session. The use of FMG sensors is a very inexpensive and easy way to detect muscle activity of the arm. This type of sensing technique only costs a few $100s, requires minimum circuitry, does not need any skin preparation, and is less sensitive to electromagnetic interference. Therefore, we think FMG is a reliable substitute of EMG in telerehabilitation systems. A total of 10 healthy subjects with no motor impairments participated in this series of experiments. They were aged 23 to 39, mean value of 28.8 and standard deviation of 4.62. 8 right-handed and 2 left-handed. Subjects were positioned next to the Q arm, holding the N effector with the right hand and starting with a 90-degree flexion of the elbow over the horizontal plane of the robot's workspace. No gravitational support was provided to the subject's arms, and no contact with the robot was allowed except for the handle. A 20-second stimulus was applied to the subjects through the Q arm. The stimulus was a sum of 10 sinusoidal waves in the frequency range of 0 to 2 Hz, producing a maximum displacement of 9 centimeters. This frequency range is based on natural human motion and typical rehabilitation tasks. A PD position controller with feedback was implemented to generate motion and stimulate the subject's hands. Each experimental session consisted of 5 EOP estimations per level, with a total of 25 randomly performed measurements per session and per subject. The levels were set at 5, 20, 40, 60, and 80% of the maximum grasp force for the first trials, or full arm FMG for the second trials. The first 5 seconds of each signal were discarded due to sensor calibration, signal conditioning, as well as to give time to subjects to hold the handle. In our trials, visual feedback was displayed to participants during stimulation and online estimations, so they could follow the 5 personalized levels of grasp force, or full arm FMG. All reference lines are based on the maximum level of the subjects, which are obtained at the beginning of each session as a calibration procedure. To measure maximum grasp force, subjects were asked to hold the handle, applying their maximum grasping strength, and for maximum values of FMG at biceps and triceps, subjects were asked to flex and extend their elbows respectively with maximum effort while holding the handle, and the handle was locked in position to maintain a 90-degree flexion of the elbow. Here you can see a time profile of online estimated EOP values of a subject at 80% of maximum full arm FMG. EOP converges to a maximum value after a few repetitions of the stimulus. An online estimation uses a simpler method of integration that allows the computation in real time, but lacks some accuracy. So we used an offline estimation algorithm for data processing and analysis. All EOP estimations were performed over 2 sessions for each of the subjects, one for grasp-based estimations and another for full-arm FMG estimations. Data resulted in 500 sets of signals from the 2 sessions, and here we can see the EOP means at the 5 levels of grasp force and full-arm FMG-based estimations per subject. Now we want to compare the differences in estimations between the 2 methods. We ran 2-factor ANOVA tests to find differences between grasp force and full-arm FMG-based estimations of EOP. An alpha factor of 0.05 was chosen for all tests. We found out that full-arm estimations were significantly greater than grasp-based estimations for all levels. Therefore, not only does the full-arm FMG method improve the measurement of energy absorption capabilities of the arm, but it also allows the use of greater amplitude forces in human-robot interactions without inducing instability. We are currently comparing EMG and FMG-based techniques and using both types of signals as inputs of machine learning algorithms. We hope this will help improve real-time estimations during human-robot interactions. Thank you for your time, and don't hesitate to send me your questions to andres.ramos@queensu.ca. Goodbye.